Hello everyone, my name is Mert Tostalı. I am a PhD student from Boston University. Today I will present our recent work which we call VAIF. Developers use instrumentation such as logs to diagnose performance problems in their distributed applications. However, it is difficult to know a priori where these log statements are needed for the problems that may occur in the future. So in response to this problem, we present variance-driven automated instrumentation framework, which we refer as VAIF. In response to newly observed performance problems, VAIF searches possible instrumentation choices, and to work, it combines distributed tracing with insights about variance decomposition. Diagnosing performance problems in the applications is extremely challenging. And with the emergence of the distributed applications, the problems now can be anywhere. It can be due to one of the many components, or it can be due to inter-component interactions. As a result of this, developers heavily instrument their distributed applications, but exhaustively recording all possible application behaviors is infeasible due to resulting overhead and too much data. As a result of these issues, applications usually contain lots of log statements, but rarely the right ones when you need them. To reduce diagnosis times, researchers have developed automated techniques for performance diagnosis using instrumentation. However, they are not directly applicable to performance diagnosis. First, they focus on correctness problems, not performance problems. For example, log20 enable logs to differentiate unique code paths. However, fast code paths may not need to be differentiated for performance problems. And for the slow ones, even though they are differentiated, they may need additional log points to pinpoint problem further. And other works such as log-scare are not designed for distributed applications. And they also ignore critical context information, which is request workflows. And workflows are necessary to know information of services, processes, and methods involved in a user request. As a result of these issues, log-scare may enable logs in the areas that are not really performance sensitive. So we first drive key requirements for any automated logging frameworks in performance diagnosis. Past research has argued that the logs needed for one problem may not be useful for others. This leads to a tussle between what kind of log statements should be enabled by default. To answer this, we drive the first requirement, which is automated logging frameworks should allow logs to be enabled selectively. And second, even modestly sized distributed applications contain thousands of possible log points in a single request. So automated logging framework should narrow down the search space such that it doesn't take long to localize the problems. So today, tracing infrastructure captures huge amount of data. For example, Canopy from Facebook captured gigabytes per second trace. So even though when the solution is there, it might not be possible to find the log points that are referring to these problems. So the last requirement would be any automated logging framework should explain these logging decisions to the users. We next discuss insights and enablers that let us to address these requirements. First, requests with similar critical paths that are processed similarly by the application will have similar response times. An existing use of this is that operators generally use different performance counters for different operations in their system. For example, read and write operations will have different performance counters. And second, we use distributed tracing, which is an enhanced form of logging. Distributed tracing provides us the graph of journey of a request throughout the system. And with the graph given, the response time variance can be now decomposed into portions of a request. Building on these requirements and the insights, we next present our approach. We first group request traces, and then we identify the traces with the high variance. Then we localize this variance into the portions of the request. Then VAIF drives this hypothesis in the form of enable and disable trace points. So VAIF drives hypothesis in order to differentiate groups with the high variance, and also it can isolate the high variance to the portions of the request. Let's walk through an example. In this one, we study an example for high variance due to caching operation. We collect traces and group them by their type. And then within this request, we realize there is a high variance in the response times. Then VAIF localizes this high variance into the portions of the request, which corresponds to storage node read accesses. And then VAIF will enable trace point, which is caching trace point, and then it will differentiate cache hits from the cache misses. And further, VAIF can then focus on the consistently slow groups by focusing more on the cache miss regions and can enable more trace points in that region. The goal of the VAIF is to, when the developer faces a problem or suspected of something, she pushes a button and then VAIF automatically enriches traces with the additional trace points. And architecturally, we have two planes to work. On the top, you see control plane, which realizes the control logic, and we will walk through it in the next slides. And second, on the bottom, we see instrumentation plane, which implements the control logic's hypothesis in terms of enabling and disabling trace points. And VAIF works in a continuous loop in response to performance problems. So in the first part of the loop, VAIF collects traces from the instrumentation plane. And then control logic comes into play, and it tries to identify hypotheses of which trace point should be enabled next in response to performance problems. And it does so while trying to find potential problem. For this, it uses summary statistics such as mean or variance and find potential problems. And then it uses edge latency distributions to decide where to enable leave trace points. And it uses search components to decide what to enable. And next, these hypotheses are sent to the instrumentation plane component such that trace points are enabled or disabled. VAIF maintains a history of its decisions and their effects under the data structure, which we call hypothesis forest. So in this example, we see a tree from this forest, which corresponds to the VM list request. And VAIF first starts with the initial expectation that identical request types should perform similarly. So in this case, VM list request should perform similarly is a high-level initial expectation. And it collects traces and groups them by their request types, and then it iteratively derives hypotheses, so enable new trace points to refine these expectations. For example, in the next round, we will drive our hypothesis, and the refined expectation will be VM list with cache miss should perform similarly. And in the next rounds, we will collect more traces, and we will be looking for more potential problems, and this cycle will go on. To know what can be enabled on behalf of a group when there is a potential problem, VAIF has an offline profiling phase where it constructs the data structure we call search space. Search space constitutes the set of paths observed in the request workflows. And at runtime, when there is a problem, VAIF employs search strategies, and we present two out-of-the-box search strategies. First of which uses a binary search strategy, which we call flat. And the hierarchical search explores top-down. So it first enables the children, and then it goes and tries to explore grandchildren and so on. Let's now talk about VAIF's output and how operators would use it. The first output is the new traces that are enriched with additional trace points needed to localize problems. During the time of a problem, developer will be able to take a look at the trace, and hopefully she'll be able to find out that the trace point corresponding to the problem is already enabled by the VAIF. And second output is a tag attached to each trace containing the corresponding tree from hypothesis forest that explains the results of hypothesis. For example, it may show that enabling a trace point around some regions differentiated groups, increasing predictability for one and unpredictability is isolated for the other group. And last, we provide CLI to the users, using which the operators or developers can query the hypothesis forest directly to identify group of requests with a high response time variation or which are consistently slow. Using the CLI, operators can identify all groups and request types with statistical summaries, and also they can get the ranked ordering of these groups. So let's talk about the implementation of VAIF. VAIF has a modular control plane which is shared by all of the applications that are running with the VAIF. And it implements the search components and the control logic of the VAIF, which we implemented in the Rust language. And on the bottom, we have the instrumentation plane. It only requires modifying existing tracing infrastructure, such as OS profiler in the OpenStack and Xtrace, which we merely modified for the conditional checks that are checking whether the trace points are enabled or not. Overall, VAIF serves as a fundamental step for developers to diagnose performance variation, which is to localize them to a specific area of the system. So the table provides an overview of the cases we found during our experiments on 2 different applications while we were running VAIF. And VAIF was able to find interesting performance issues while reducing trace sizes by 90%. And for the sake of time, I will just study one case from this table. All instances on the OpenStack can be listed using the command vmlist. And VAIF finds that vmlist requests show high variance. And then when we get the slowest request from this group of traces and we query the hypothesis tree with this request, we find the following hypothesis. VAIF first came up with the hypothesis that identity service, in particular the keystone, is showing a lot high variance. And next, VAIF also came up with the hypothesis that get all function in the source code of OpenStack is showing a lot high variance and high latency. And later we found and corroborated these both issues in the bug reports of developers' mailing lists. In this talk, we presented VAIF, a distributed tracing framework and variance-based control logic to automatically adjust instrumentation for performance diagnosis in the distributed applications. And thank you for listening to my talk.